Hi, I'm Lut Maliki, and I'll be presenting our work on the development of an ultra-wideband photonic VCO and synthesizer. This work was performed by my colleagues, Danny Eliyahu, Abdul Karim El-Amili, Robert Moss, George Kasayan, Anatoly Savchenkov, and Sitare Ganji at OEwaves. OEwaves is located in Pasadena, California, and it's a company that was spun out of NASA Caltech's Jet Propulsion Laboratory back in 2000. We provide products and solutions that address the needs of industries such as defense, aerospace, communications, and commercial industries, and apply our unique photonics capabilities to provide these solutions and products. VCOs are well known in the community and they're used in a variety of applications. I have just named a few of them here. And these are applications that typically require higher performance for the output of the VCO. In other words, the noise of the produced signal must be low, and in many of these applications. Recently, there has been a migration of frequencies of these applications, this type of applications, to higher frequencies, away from RF and microwaves to millimeter waves and beyond. And this has represented a challenge for the conventional VCOs because typically oscillators made with conventional approaches to produce a spectral purity which degrades with multiplication of the frequency. The higher the frequency goes, the worse is the noise of the oscillator. So this has been one of the problems. The second problem is that the bandwidth of tunability for these type of oscillators must be at least 10% or more of the center frequency. And that means that by the time we get to 100 gigahertz, in many of these applications, requirements is 10 gigahertz bandwidth, and that's difficult to achieve. Conventional approaches may have this challenge. However, this is not a challenge in principle for photonic approaches, because in the simplest approach, if we get two lasers that are separated by a certain frequency, say delta nu, and delta nu can be any frequency in the RF to millimeter waves or terahertz for that matter. And if we introduce the output of these two lasers into a photodetector, since the photodetector is a quadratic detector, it mixes the optical signals and the beat between the two is generated. And this beat, of course, would carry the same frequency as the frequency interval difference between the two lasers. One of the advantages of doing this is that we can easily tune the laser wavelength and therefore its frequency, and as such, tune this over a very wide bandwidth. But most importantly, since the noise of the laser does not change with frequency, as we tune and change the frequency of the oscillator, the noise remains the same. So this is very different than conventional cases where, as I mentioned before, noise degrades with increasing frequency. The challenge, however, here is that in order to get a high performance or low noise output, we need to have very low noise lasers as well. In fact, there's a 3 dB loss in the noise of the oscillator compared to the noise of the laser. So we have to start with very high performance lasers, and that is very difficult to achieve, especially if we also require tunability. At OEwaves, we have a technology which is based on whispering gallery mode resonators. These are optical resonators that are very small, the size of a millimeter or so, and they can have Qs of 100 billion or higher have been demonstrated. And with this kind of a Q, the bandwidth of the mode is rather narrow, and it can be used as a filter to filter out noise. And the way we put this to advantage in our lasers is that we start with a semiconductor laser and couple the light of the laser to this very high Q resonator, and with the mode, whispering gallery mode, which is very high Q. And some of the light from the resonator backscatters into the laser, and as a result, the laser is injection locked to the mode of the resonator, and its noise is dropped significantly, so the output is going to be very low noise. In fact, as is shown in here, starting with the DFB semiconductor chip, we can reduce the noise by 6 orders of magnitude, or 60 dB. With this kind of a laser, we have built an ultra-wideband photonic VCO that operates from 1 to 110 gigahertz. We can set the frequency at any value here, and we can tune it from 1 to 110 gigahertz. So it's both a VCO and can be configured as a synthesizer. The power output is about -5 dBm, and the performance of the free-running oscillator is shown here. The other advantages of this oscillator, aside from the fact that it has noise that is significantly lower than the state of the art at higher frequencies, is that the time jitter is very small, and the spurious value is very small, and it operates with 6 watt of power. The block diagram that's shown in here demonstrates how we implement this technique. We have a control electronics that can change the frequency of the two lasers, and therefore adjust it accordingly to provide the output frequency that is desired, simply by changing the voltage and controlling this with a computer. With this technique, we have managed to show that the VCO not only has very low phase noise, and not only is the same for all values, the phase noise is the same at all values of frequency, but also is very stable. This is the free-running oscillator that the noise is shown over several hours, measured several times, does not change. Here, this plot demonstrates tuning of this oscillator from 1 to 110 gigahertz at the steps of 10 gigahertz. Of course, the step is what we chose, but it is selectable by the user to any value that is desired. Now, at lower frequencies, for example, at 8 gigahertz, the free-running oscillator does not have good performance. By good, I mean compared to, for example, a multiplied 100 megahertz oscillator. So as such, then we can take the free-running oscillator, VCO, and lock it to an external 100 megahertz oscillator. Here is a Wenzel oscillator. And we can realize a performance that remains the same from about 100 kilohertz out, but within the bandwidth, which is about 20 kilohertz, the performance, of course, is the performance of the external reference. In this fashion, we can demonstrate that the performance of the VCO, OEwaves VCO, shown with these solid lines, is superior to that of the state-of-the-art performance of the Keysight synthesizer, Keysight PSG, that at 60 gigahertz and 90 gigahertz. And in the case of Keysight, you clearly see this penalty of the multiplication as the noise goes higher and higher. In the case of the VCO, the noise remains the same from 100 kilohertz out, and it's also lower than the noise within the bandwidth of the locking bandwidth. And finally, the oscillator clearly can also be tied or locked to an external clock. Here, a rubidium clock shown in green, and the oscillator locked to it shown in orange. So in summary, we have shown a unique photonic VCO that is capable of producing very low phase noise and a phase noise which is independent of frequency. The VCO currently operates at about 110 gigahertz, and because it can tune across this entire range, it can be operating as a frequency synthesizer. The range of 110 gigahertz is limited by the bandwidth of the photodetector used. Currently, photodetectors with bandwidth as high as 300 gigahertz and beyond are coming into the market. And by simply changing our current detector to these, we can extend the range of frequency of this wideband VCO. With this, thank you for your attention, and I close my paper.